Hi everybody, today's video is going to be focused on working through particle motion problems, and a lot of this work should feel very familiar. We did a lot of work during first semester with particle motion, and in particular in those problems we were given the position function and then asked to analyze the position, velocity, and acceleration. So these problems are going to be very much the same with one difference. In the problems we're going to be doing now, you're usually going to be given the velocity function for the particle that's in motion. And so we're going to talk about, now that you're given velocity, how do you find out about the motion of the particle? And so we'll look at problems where you're given a function, a graph, or a table of values. So again, the big difference here is before we used to start with position. Now we're going to be given velocity and have to use our knowledge of both derivatives and integrals to analyze this motion. So first we're going to do a quick review of the vocab. So when we're talking about the direction the particle is moving, we're going to be looking at velocity. So we're moving right when our velocity is greater than or equal to 0. Now that's if we're analyzing the function. If we're analyzing the graph, we're going to look for where velocity is above the x-axis. And I'm sorry, this is going to be kind of small because I'm trying to shove it in there. So we're right when velocity is greater than or equal to 0. On a graph for velocity, that looks like velocity being above the x-axis. For moving left, we have velocity is less than or equal to 0. On a graph, we have velocity below the x-axis. And then for the last part, we're going to be stopped where velocity is equal to 0 if we're given a function. And on a graph, that's going to be where velocity crosses or touches the x-axis. And again, that's a review. We knew that back in semester 1. When we're talking about instantaneous velocity, that's just our velocity function. Speed, hopefully you remember, is the absolute value of velocity. Remember, velocity is going to give us the direction as well, so if we want speed, we just take the absolute value. Now, if I want average acceleration and all I have is the velocity function, if I'm asked for the average acceleration over the interval from a to b, I'm going to use slope here. So we would use our velocity function, v of b minus v of a, all over b minus a. Instantaneous acceleration, that's our derivative of velocity, which is our function a of t, our acceleration function. And then the last piece we had was speed increasing or decreasing. So here's where we needed to look at the sign of both velocity and acceleration. And we said if v of t and a of t have the same sign, then we know the speed is increasing. Okay, on the other hand, if v of t and a of t have opposite signs, then we know the speed is decreasing. So again, there's nothing new here. The only difference is usually we're going to be starting from the velocity function instead of the position function. Now, given all that vocab, here's the 4 questions you're most likely going to be asked. So given a velocity function v of t, and they're typically going to give us some initial position. Right now we'll call it c. So the first thing they could ask us for is the displacement. Hopefully by now you guys realize, let's say I'm going to use my interval again from a to b. Displacement we just know is the integral from a to b of v of t dt. And this has come up a lot when we've been interpreting integrals. You guys have had to interpret the integral of the velocity function, which we said is the displacement. Now, something new. Remember, displacement just tells me how far I am from where I started. So I'm going to make a note here. And so I'm going to think about if I had a particle, let's say the particle went, I don't know, let's say 2 meters to the right, and then backwards 1, and then forwards 3 more. Right? We would say the displacement is going to be 2 minus 1, which is 1, plus 3. We would say the displacement is 4. Right? It's 4 units away from where it started. However, total distance traveled, when we're looking here, now we're going to take the integral from a to b of the absolute value of v of t dt. Now the idea is don't tell me how far I am from where I started, but add up all these values. So in other words, I'm going to take now 2 plus the 1 that I traveled plus the 3, and now I've traveled a total distance of 6. So that's kind of the difference here. So total distance traveled is going to be integrating that absolute value. Now, the actual position at a given time, we're going to start with our initial position, c, and then we're going to add the displacement. So the integral from a to b of v of t dt. So my actual position, we're going to say, is initial position plus the displacement. And if you can't read that, that says initial plus the displacement. So we have our initial position c plus our displacement, which we know is the integral from a to b of v of t dt. Then the last thing we have here is average velocity. Hopefully this word average velocity makes you think average value. So if again we're looking over that interval from a to b, our average velocity is going to be 1 over b minus a times the integral from a to b of v of t dt. So this is what we're going to need to be able to do, and in the rest of this video we're going to actually walk through some problems and do this work. Alright, so let's first flip over and we're going to look at a velocity graph. So the graph shows the velocity, so I'm just going to make myself a note so I remember this is a velocity graph, of a particle that is moving along the x-axis on the interval between 0 and 8. Okay, and it's telling us velocity is inches per second. So let's take a look. It says for what intervals is the particle moving to the right? Well, we said right is where our graph of velocity is above the x-axis. So I would say the particle is moving to the right, and I'm going to say it's on the interval. I'm above the x-axis from 0 to 3, and by convention we make that a closed interval. And then I'm also above here from 7 to 8. So those are my intervals, and now I'm asked to justify. And here we want to be careful. In our justification, we don't want to say because it is above the x-axis. We want to be really clear, and we're saying it's moving to the right because velocity is greater than or equal to 0 on these intervals. So we want to be really careful with our explanation there. All right. Now, that one's pretty straightforward. For part B, it says, for what intervals is the particle slowing down? So we actually have to take a couple cases into this account. So for what particles is, or intervals, excuse me, is the particle slowing down? We said it's slowing down where velocity and acceleration have opposite signs. So I have to look for the first case, and I'm just going to make myself a note here. The first case is where velocity is positive and acceleration is negative. Now for us, velocity greater than or equal to 0 means it's above the x-axis. Acceleration less than 0 means where does velocity have a negative slope? So I'm going to kind of highlight here because I think it helps to see. Velocity is greater than or equal to 0 over this whole interval, but the only part where it has a negative slope is right here. So that would be, let's see if I can not smudge that. That's going to be the pink part there. So I would say the particle is slowing down. On my interval, let's see, on the interval from 2 to 3. And I'm going to say because v of t is greater than or equal to 0. Now, I'm not going to say a of t is less than 0 because I don't have an acceleration graph. I want to answer it in terms of what's happening in velocity graph. So I'm going to say because velocity is greater than or equal to 0 and the slope of velocity is negative. Because that tells me that acceleration is negative. Now, I have another case to consider here, right? I could also look at where is velocity less than or equal to 0, but acceleration is positive. So let's figure out where that would be. I'm going to do this one in green. So velocity less than 0 means I'm below the x-axis. Acceleration positive means I have a positive slope. So in this case, we could also say, now I could have made this one response, but I wanted to clearly highlight the two cases here. So I would say the particle is slowing down on the interval from, 6 to 7, because my velocity is less than or equal to 0, and the slope of velocity is positive. So those are two cases where I could be slowing down. All right, for the next one, when does the particle change directions? So I need to show where velocity is 0. I'm going to make myself a note. That'd be where velocity equals 0. And it changes signs. That's really the biggest thing I'm looking for, is where does it change signs. So I'm looking for where does it cross the x-axis. So I'm going to draw an arrow there. It crosses the x-axis. So here we would say the particle changes directions at time, let's see, t equals 3 and t equals 7. And I would say because velocity, v of t, changes signs. At these values. All right, next one says suppose the particle's position at t equals 0 is 9. So here they're giving us an initial position. And I hope I'm not writing too small. So an initial position, it wants to know the position of the particle at t equals 8 seconds. So we said to get its position, we need to add the initial position plus the displacement. So what I'm going to do is take my initial position, which is 9. Now here's something important. We know the displacement is the integral of velocity. And here's where we just have to be a little careful with the bounds. Since this initial position was at t equals 0, that has to match my lower bound. So my lower bound has to match that time. Then since I want the position at t equals 8, that's going to be my upper bound. So now we could use geometry to figure this out. And for the sake of time here, I'm going to leave you to calculate that. I don't want to necessarily take the time to do that calculation. All right, and part E now asks us the total distance traveled by the particle over the interval. Whenever I see total distance traveled, I know I'm integrating from 0 to 8, and I'm going to do the absolute value of v of t dt. What that means is that every value that used to be below the x-axis, right, we're going to treat as a positive. So in other words, if I set this up, I have my first integral from 0 to 3. I see I have a trapezoid of height 3. So I've got h over 2 is 3 over 2. My top base is 1. My bottom base looks like 3. I'm going to, again, treat this as a positive now because I'm doing the absolute value. So I'm going to add, let's see, the height of that one is 3 as well. Base 1 is 1, 2, 3, 4. It looks like 4 plus 2. And then we're going to add that triangle at the end, which is 1/2 times 1 times 3. So it looks like I get 3/2 times 4 plus 3/2 times 6 plus 3/2, which is 6, hopefully plus 9, plus 1.5. And it looks like I'm going to get 16.5, and those units are going to be inches. Okay, and an important note there is to include the inches. Remember, when we're integrating, we're multiplying, so our units are really going to be seconds, which is on the x-axis, times my inches per second, which is my velocity. So when I multiply, I get units in inches. Now the last one just asks for the displacement. We really set that one up in part D, so we'll leave that for now. All right, let's go ahead and flip. Now we're going to look at one where we have a table. And this is a calculator problem. You'll see our little icon there, so we can use our calculator, to help us out. So here we have Johanna jogging along a straight path. We're looking at the interval from 0 to 40, and her velocity is given in the table below. And you can see our units for velocity are meters per minute, and our time is minutes. So it's asking us to estimate the value of v prime of 16. So it's asking us to estimate the derivative, and we use slope to estimate that. So to estimate a derivative, we're going to use our slope. So if I were looking for 16, that's going to be in between 12 and 20. That's my closest interval around 16. So we're just going to do v of 20 minus v of 12 over 20 minus 12. So velocity at 20 is 240 minus 200 all over 8. So 40 over 8. Is going to give us 5, and now we're going to be very careful with our units. Our units are going to be, let's see, we had meters per minute over minutes, so we're going to have meters per minute squared for that problem. Again, if you're given units, make sure you include them with your responses. Now, in part B, it's asking us, using correct units, to explain the meaning of this integral, 0 to 40, of the absolute value of v of t dt. This should absolutely jump out at you, that absolute value, and we should remember that's total distance traveled. So if I'm doing the meaning, I'm going to say the integral from 0 to 40 of v of t dt represents the total distance that Johanna jogs. We're going to include our units, so the distance is going to be measured in meters. And then the last thing we had to put is the time from t equals 0 to t equals 40 minutes. Okay. Now, the second part asks us to approximate the value of this integral using a Wright-Riemann sum. Because we hit that so hard in the last chapter, I'm not going to worry about the calculations. What I do want us to be careful of is, again, that absolute value means when I'm setting up my calculations, right, I'm using the 4 subintervals, so I'm going from 0 to 12, 12 to 20, 20 to 24, and 24 to 40. It's a Wright-Riemann sum, so I'm going to grab my 200. At 20, it's 240. Now here's where I'm being careful. 24 is a negative 220, but because we're doing the total distance traveled or the absolute value, we're going to treat that as a positive now. And then our calculations would follow just the same. So again, I'll leave you to do that calculation, but that's how it would work. All right, now in part C, they're saying Bob is riding his bicycle along the same path, and they give you his velocity function. So they're defining a new velocity function for Bob, and they want us to find his acceleration at time t equals 5. So if this is velocity, I know to get acceleration, we're going to do b prime of t, and in this case, we're going to do b prime of 5. Now, I'm not actually going to worry about finding this derivative. I'm going to use my calculator to help me do this. So what I'm going to do is in y equals, I'm going to put in, actually not in y equals, excuse me, I'm going to go math 8. So I'm going to do the derivative with respect to x. I'm going to plug in my velocity function of x cubed minus 6x squared plus 300. And I want to evaluate that when x is 5. So I'm going to use my calculator to do this for me, and I'm going to get 15. And my units, again, are going to be meters per minute squared. So now the last part says, based on the model from part C, find Bob's average velocity. Again, hopefully that average velocity reminds you that what we're really doing here is average value. And we're on the interval from 0 to 10. So I'm going to set this up. It's going to be 1 over 10 minus 0 times the integral from 0 to 10 of b of t dt. Now, one thing I want to make a note of here that's going to be really important for on the AP test as well, even though this is a calculator problem, it's really important for you to write the integral that you're evaluating. If you just have an answer, that may not be sufficient to get credit. They want to see that you know the correct thing to evaluate. So we always write this down, even though we're just going to put it into our calculator. So now I can go over to my calculator, do my alpha y equals, I have 1 over 10, then times math 9, the integral from 0 to 10 of, let's see, velocity, and again that's x cubed minus 6x squared, whoops, plus 300, and I'm going with respect to x, and I get 350. Now here we have to think about the units. 1 over 10, that's basically saying 1 over my minutes. Now the integral is multiplying, let's see, it's multiplying meters per minute times minutes. So if we simplify that, our integral is giving us units of meters, but now when we multiply by that 1 over 10, our units are going to be meters per minute. And those will be the units for that problem. So for right now, we're going to stop this video. I know there's another problem left. We'll talk about that one in class, but I'll also make a video of it so that you can watch it later if need be. But for now, we're going to stop this one. That's been plenty of content. So again, make sure you've got really good notes. Come prepared to ask any questions that you have, and I will see you in class. Thanks.